Hello students, let's begin lesson 2. Section 1, complex numbers. This corresponds to section 1.3 of our textbook. Here's the definition. A complex number z is defined as x plus yi, where x and y are real numbers, and I is a mysterious number with this property. I squared is equal to -1. Now there's no such real number with this kind of property. If I had been a positive real, then I squared would have been positive. If I had been negative real, then I squared would have been still positive. So this is impossible for any real number. That's why it is called the imaginary number. And the real numbers x and y are called the real part and the imaginary part respectively, for obvious reason. I comes here, so that's called the imaginary part, and this one is purely real, so real part. And special case, when y is equal to 0, then this part drops out, so we just have a real number. So complex number system actually includes all the real numbers. Sometimes we use this kind of notation, x as the real part of z and y as the imaginary part of z, but we're not going to use these kind of notations in college algebra level. In Math 1600, in trigonometry we will, so do not completely forget about these kind of notations, but at this moment, let's just stick to the definition, x plus yi form. Alright, we went through the definition, let's do some computation. Algebra of complex numbers, we can add or subtract any complex numbers, kind of like these, treating I as any character and taking the like terms together. Too trivial. So trivial that I'm not going to spend any class time on it. Let's go to multiplication, and this has some wordy computation here. We have a binomial times binomial basically. So we can FOIL those out, and then you're going to encounter I squared. Whenever you have I squared is equal to -1. That's the definition, remember? So b1, b2 times -1, so we ended up with the sign change. So that's what this I squared is doing. I squared is -1, consequently a sign change. Remember that, and then you can do all kind of multiplication as well. Let's see, too many characters here, too many symbols. It's hard to understand what is going on, so let's do it with a concrete problem, and here's a nice one. Okay, how do we calculate this? Okay, let's FOIL it out. First, 3 times 4i. And then outside, 3 times 1. Inside, I times 4i. Finally, last, I times 1. Okay, we did the FOILing, and we have to take the like terms together, but before that, don't forget this I squared becoming -1, so times -1. So in the end, what does it do? It changes the sign. Oops, sorry about that. So I squared does a sign change. Okay, we're almost there. Take the like terms together. 3 minus 4 is -1. 12i plus I is 13i. I just looked at, so I got 13, so I ended up saying, okay, anyway, we have the answer, -1 plus 13i, and that must be correct. Yes, indeed. So here is complex multiplication. And this one here is too symbolic, so it's a little bit difficult to follow. However, it has a meaning. It proved that the complex number system is closed under multiplication. You see, the result here and the result here is also x plus yi form. This is the real part, and that's the imaginary part. Okay, we don't need this any longer. And let's go to division. Division is much harder. And here is symbolic computation. Oh, but wow, it's really difficult to follow. There are too many symbols. So instead of going through this, let's work out a concrete problem. Let's do this. We have a fraction here, so let's increase the font here so that we can read this thing better. Okay, how do we work this one out? Whenever you have to simplify a fraction, think about this. Multiplying by a same number to both numerator and denominator. That's usually the essence. In this case, I have to select that number strategically. How do I do that? The number I selected here is 2 plus I. And this kind of number is called the conjugate. And it is basically the sign change. If you have a plus bi, change to a minus bi. If this is already negative, change to plus. Basically, the sign change on the imaginary part. That's what I did here. The real part 2 stays the same, and the imaginary part is -1 in this case. Changes to +1 so that you have -I becoming plus I. If I do that, will it help? Well, let's find out. Will it really help? Let's go ahead and flip this one. 3 times 2, that's 6. First, outside, 3 times I. Inside, 4i times 2. Finally, last, 4i times I. 4i squared. How about the denominator? First, 2 times 2, that's 4. Outside, inside, and then last. Please remember we have I squared, and that's going to be equivalent to -1. So what do we have here? Let's copy and paste, and let's take care of that I squared. And I squared give me the sign change. I squared is equal to -1, so we have the sign change. Same here. That'll give me the sign change. Furthermore, please pay attention to this 2i minus 2i here. They're going to cancel each other out. And that was the design. That's why we multiply by the conjugate of the denominator. You see, this is a minus b times a plus b form. So ab term cancel each other out. So we don't have this any longer. So there you go. 4 plus 1, 5. We have a real number in the denominator. So here we go. We have 6 minus 4, that's 2. 3 plus 8, so that's 11i divided by 5. So we have 2/5 plus 11/5 I. We have x plus yi form. That's how you complete complex division. Multiply by the conjugate of the denominator to both numerator and denominator. Foil it out, so you have to do complex multiplication as well. And then take the like terms together. You have to do complex addition and subtraction as well. And then simplify, simplify, simplify. In the end, you're going to get x plus yi form. The real part and the imaginary part. In general, you can do these kind of things with all those symbols. You see, multiply by all these, and then I squared here, I squared there, will give me the sign change. And then these two will cancel each other out. So we have a real number in the denominator, no addition, just add them up, and then separate the numerator, real part, imaginary part, times I. So it works out. So what did he accomplish here? We just proved that the complex number system is closed under division by a non-zero number. So we can actually conduct division using this kind of technique by multiplying the conjugate of the denominator to both numerator and denominator and filling out. And by doing that symbolically, we prove that the complex number system is closed under division. I have many more problems here, and you don't have to do all of them, but if you can try some of them, that's going to be enough. As for the importance of this, complex division itself is important. If you can do complex division, that includes complex multiplication, addition, and subtraction all in one. So that's important. And I always write that kind of problem in the second exam of Math 1600 trigonometry. I've never written it in this course, Math 1100. But then again, that was before we changed our textbook. Now, this is included in Math 1100, so I may start writing this problem in the exam in Math 1100 as well. Or maybe not, and I may end up sticking to 1600. At this moment, I didn't make a decision. Well, I didn't write any exam problem yet. In any case, as a standalone value, complex division is important. I mentioned the name conjugate several times, and that's basically it. Changing the sign of the imaginary part, and typically we use bar to denote conjugate. As for the notation bar and another concept, modulus, those are going to be important in Math 1600 trigonometry, but not here, so I'm not going to talk too much about that. Instead, let's talk about solutions of quadratic equation. You see, you have this, the quadratic formula. And what if the inside of that quadratic formula, inside of the square root, is negative in that quadratic formula? What do you do then? Well, let's consider this kind of problem. X is equals to minus b plus or minus square root of b squared, 6 squared, so 36, minus 4ac, 4 times 1 times 10. So we have that divided by 2a, 2 times 1. So we get that. A little bit bigger font, I guess. And the inside of the square root is negative. So this is negative 4. How do you handle that? If you recognize I is square root of negative 1, you can rewrite like this. And then this can be simplified further into this. Square root of 4 is 2. So what do we have? Negative 6 over 2, so negative 3 plus or minus 2 over 2 is 1, like this. Or if you prefer to write two solutions, x1, first solution is negative 3 plus I. x2, second solution is negative 3 minus I. You can write like that too if you want to. In any case, it is possible to express the solutions of quadratic equation using i's when you have negative in the square root. How do you do that? Whenever you have square root of negative, we have the square root times I. That's the standard process. Okay, that's it. Section 1 is done. Let's meet again in section 2.